We will do that in the context of examples of reactive polymers that we are going to see next. The first example are called acrylates. 3D Systems is one of the companies that offers acrylates as reactive polymer systems for 3D printing. They're clear, clean burning, and it is possible to introduce a wide range of chemistries, some of which can be biocompatible, as in the case of these ethylene glycol based chemistries. These are compatible with stereolithography, DLP, digital light processing system, or material jetting process. The second example that we will look at are epoxies. DSM is one type of a company that offers these materials. To get high temperature properties and different mechanical properties by incorporating fillers that are strong and stiff, epoxies offer contrasting properties to acrylic. The defining characteristic of an epoxy is this triangular shaped chemical group with an oxygen present over here. That's the epoxy group. You have different starting materials and prepolymers depending upon the actual architecture of these. In terms of reactive polymers, let's take a look in this module at different kinds of polyesters. The term polyesters we've used in the context of PLA and PCl in the previous module itself. Here are the two molecules. It is possible to go through a chemical reaction called transesterification. Many of these are produced anyway by polycondensation. By using trifunctional materials, it is possible to have cross-linked materials that are PLA and PCl based. We had seen that Perstorp was the company that offered PCl under the Kappa trade name, and PLA was offered by NatureWorks LLC as one of the vendors by Ingeo. Key thing is these are biodegradable again, and they have a low toxicity, and they can be cross-linked. So there's a lot of interest in seeing how these attributes can be taken advantage not only through melt processes as we saw with FDM, fused filament fabrication processes in the module 1, but now through cross-linking reaction. And we'll take a look at what advantages and what limitations occur when you go through this route. Another example are silicones, widely used as a two-part system in conventional polymer processing. Main thing is you have service temperatures over a very wide range that can be used. In the first avatar of 3D printing in rapid prototyping, molds made of silicones were used as the starting point to create replicates of an initial master. This was then extended to directly printing. Walker is a company that produces a range of silicone-based. E-silicone from Envision Tech is something that we can look at as we move forward. So primarily you have, in the case of silicones, these SiO-based organometallic materials. Organo because of these carbon-based groups, it's metal groups that are there, in addition to silicon-based, which are metallic. Usually, you have a curing agent that is a tin-based material that catalyzes cross-linking, and you end up having these types of SiO-Si cross-links being generated in the material. Phenolics is another example, and Voxel Jet offers processes for binder jetting that are based on curing phenolics. These are naturally occurring low molecular weight components, and so when they cure, you end up having emission. Usually this group over here, this hexagonal benzene ring with this OH group, is a phenol in question. When they begin to cross-link, you begin spitting out, for instance, small molecules. This VOC emission is a typical wrap on using phenolic in conventional processing as well as in 3D printing. Fewruns, which is this 5-member ring with an oxygen atom in it, is another type of example of a reactive polymer. This is another example of a resin that is usually combined with the binder jetting process. A lot of sand-based molds are fabricated both for using Fewruns and phenolics that we saw earlier. X1 is a company that uses Fewruns as one of the offerings in their binder jetting process.